Hello everyone, how are you? How's everything? I hope everything is going well with you. So, after having a long discussion about diets and solving problems, I'm sure that you are all very familiar with the diets now and you're ready to move on to the next very fundamental nonlinear circuit component, which is called transistor. So, we have two main type of transistors. We have BJT and we have MOSFET. So BJT is bipolar junction transistor and MOSFET is field effect transistors. So we're gonna start with the BJT transistors and we're gonna see what is this amazing creature of the electrical engineers is about. So let's go ahead and see what is a BJT transistor. A bipolar junction transistor looks like this shape. If you go to store and try to buy it, it looks like this shape. It's a 3-terminal device, so it has 3 pins. The pins are named base, collector, and emitter. So B is for base, C is for collector, and E is for emitter. In circuits we show it like this usually. Usually here is the collector, see, here is the base, here is the emitter. I will explain to you later on that why do we show it like this. And here it can be also in graphs or diagrams, it can be also shown like this. It's because if you remember, diode was a PN junction. It means one p-type semiconductor and one n-type semiconductor were put together and created the diode. Transistor is made of 3 different pieces of semiconductors. One n-type, one p-type in the middle, and another n-type. Or we have a different type, this is called NPN transistor. We have a different type of transistor, we call it PNP. That one, there is a p-type here first, then there's an n-type, then there's a p-type. If you think about it, you can imagine that you can put 2 diodes back to back to each other, and the way that, imagine you have 2 NP junctions, you have put them back to back. This one, the way that N is on the top, P is in the bottom, and the other one, the way that P is in the top, N is in the bottom. So you will have an NPN transistor this way, but it's not actually like that. I'm just trying to give you a way to try to imagine it, how it's made. As I said, it's a 3-terminal device that it does have very amazing characteristics that we're going to go over them one by one. Keep this shape in mind, we're gonna use it a lot. Transistors are used in digital logic circuits a lot. They are used in amplifier circuits. And of course, they are used in high frequency analog circuits a lot. And as I was telling you, they are made out of layers of semiconductor materials with different dopings. And we have NPN and PMP. Look, this in the circuit level, NPN is shown like this. PNP, this arrow is going to be on the top. So when the arrow was on the top, it means it's PMP. So in the circuit diagrams, when you want to show transistor, we always use this shape. Base is always here in the middle. Collector is on the top. Emitter is here in the bottom, and the arrow is always with the emitter, right? So when we have, this is an NPN. When we have PMP, the arrow will be right here on the top, not on the bottom. If you want to have an imagination of what does a transistor do in a circuit, we can try to imagine it as a valve. Why? Let me remind you of something. When we were talking about sources, voltage source and current source, you imagine that I was telling you that we have two types of sources, right? We have dependent source and we have independent source. The batteries that we use in the circuits are the independent sources that we used to use a circle to show them. But we also had dependent sources, right? That we used a diamond to show them, dependent sources. Transistor is a dependent source. What kind of source? It's actually a current-controlled current source. I think you remember when I was telling you CCCS and VCVS and things like this. This is current-controlled current source. It's like this. Look, imagine it's a valve, okay? It's a valve, big valve. It's a big pipe, for example, that some liquid wants to go from here, collector, to the emitter all the way. But the valve is here at the base. So if at the base we close the valve, this current, this flow of the liquid cannot pass. If we open the valve, the flow will pass. So now, what does open and close this valve? The current at the base does that. So if there is some current in the base, it means that the valve is on. So the current can flow from collector to the emitter. It means that transistor is on. If there is no current here in the base, it means the transistor is off. So nothing can pass from here to here. As simple as this is the main objective of using a transistor. It's we're going to have a control over the signal using another signal. So this could be the basis of the automation later on, because when we're trying to automate the systems, we don't want to switch them on and off ourselves. We want the circuit itself to switch things on and on when it is needed. So how this switching must happen? There is nobody to physically turn on and off a switch. So there will be it has to happen using some current or voltage. So those sources need to be either controlled with currents or voltages to be turned on and turned off when we want them. Like imagine the air conditioning at your home. You all have an automatic system, like you set your temperature and you trust that when the temperature goes higher than the set temperature, your air conditioning starts to work. And when it reaches this temperature, it doesn't go below that. Why? Because the air conditioning stops working. So we don't do it. You don't do it manually. Maybe before, when these automatic systems were not there, your parents or grandparents, they needed to turn on and turn off the cooler and when it was getting cold, turn it off. When it was getting warm, turn it on again. But now your system does it for you. But how this system orders the compressor to turn on and turn off, it measures the temperature using a sensor that it has here, and there is a basic logic unit, there is a processor, a controller that compares the temperature that gets from the sensor with the set temperature that you set in the system. Then if the condition was met, if the temperature was higher than the set temperature, then it sends a command to the actuator, which is your compressor on the air conditioning, and says, turn on, we need your cool air, the weather is getting warm. All of this is happening using some currents. Like when it wants to tell them, okay, turn on, it means it's gonna send some, you can imagine it this way, that it's sending some current to the base of a transistor there, and that transistor is gonna let the current pass through the compressor itself. In real life, that is not done using a transistor actually for air compressors. It's done using some contactors or some PLCs or things like that, some smart relays. But the basis of the operation is the same thing. So you have so many different automatic devices around you in your lives, right? A lot of things like your laptop, your phone, that have your cars, they have all kind of automation involved, that the backlight is being adjusted based on the light in the system, like all kind of these things. There are lots of sensors, actuators, that the system is automatic. So there are many switches turning on and off by themselves. It's not by themselves. There are cool non-linear elements involved in all those circuitries that are involving transistors, or now more advanced ones, or a combination of several transistors. So this, I told you all these things to understand why actually do we need to have such nonlinear components in our circuits. So let's go back to the operation of the transistor. This device, this transistor, has 4 different modes of operation. Maybe 3 of them are the main ones. It has cutoff, it means it's off, the transistor is off. When emitter base junction and the collector base junction are both fed in reverse, this current is going backwards. It's active when emitter base junction and is fed forward, but collector base junction is fed in reverse. And it's in saturation when both of them are fed forward. So for now, just keep it in mind. I will explain to you later what do I mean by reverse and forward. Because look, imagine this component. There are 3 terminals: emitter, base, collector. Okay, so here is, this one is called emitter base junction, this one is called collector base junction. You remember of PN junctions that we talked about in this semiconductor, like each of them is a PN junction, right? So when I say forward, it means it's current is going this way. When I say reverse, it means going the other way around. So in the cutoff mode, the emitter base junction is fed in reverse, means current is this way. And collector base is also fed in reverse, it's going this way. But in the active, no, the emitter base is gonna be forward, it means the current is actually going towards this direction. But because I had promised you that I'm gonna cut to the chase, okay, so forget about it. I'm gonna tell you exactly how it works. These are the 2 types of the transistor that I told you. This one is NPN, this one is PMP. You remember what was the hint to remember in NPN? The arrow is down. In PMP, the arrow is up. And emitter is with the arrow. So when arrow is down, collector is up, emitter is down. When arrow is up, emitter is up, collector is down. Base is always here in the middle. Okay, so in a circuit, they are actually placed like this. So collector is actually connected to some voltage, emitter somewhere, and base to somewhere. There is something that you should understand about the transistors. The current at the emitter equals to the current in the collector plus the current in the base, which makes sense, right? Some current is coming this way, some current is coming from here, so this current is this plus this. But there is something also super interesting. Usually, like whenever we are in the active mode, the current in the collector is almost always like 100 times more than the current in the emitter. But what is this 100 times? It's called beta. Say IC equals beta IB. This beta is one of the characteristics of the transistor that is always given to us. So most of the time it's 50 or 100, something around this value for NPN. So when I say IC equals beta IB, it means this current in the collector is 100 times more than the current in the base. So, question for you. So, what is the relationship between the current in the emitter and the base? We said current in the emitter is IC plus IB. So, IC itself is 100 IB plus another IB, so it's going to be 101 IB, right? So, the current in the emitter is a little bit more than the collector. How much is that a little bit? Is equal to IB. So this one will be like 101 times IB. This one will be 100 times IB. So the current in the collector and emitter are almost equal, with the little difference. That little difference is IB. Just remember one thing. All of these equations are for the active mode. This beta is I want to say the most important thing, but to be honest, transistor is not a very hard component to learn. Technically, it's the only thing that you should know about it. So in this component, the current in the collector is beta time more than the current in the base. And one more thing I want to tell you. You see this arrow? This arrow works actually like a diode. So the voltage between B and E is 0.7. Do you remember we had the VD in the voltage drop at the diode 0.7? Here it is the same. This arrow is working like a diode. So the VB is 0.7 more than VE. Here in the PNP, this VE is 0.7 more than VB. So keep these two things in your mind. Arrow works like a diode, okay? And the current in the collector is beta times more than the current in the base. And this beta is given to you in all questions. It's gonna be given to you most of the time 100. So imagine that most of the time IC is like 100 times bigger than IB, and this IE will be 101 times bigger than IB. There are some equations that you will always see in your book everywhere, that like IC equals to IS e to the power of VBE over VT. Okay, so it's telling us that IC, the current in the collector, is a function of this voltage here in the transistor. But don't worry about it too much, okay? Do not worry about it. What you need to worry about is this part. IC is beta IB, so IB will be 1 over beta IC. IE is IC plus IB. And as you can imagine, IE will be beta plus 1 over beta IC, of course, right? But since beta is usually a big number, so this number is almost 1. So IE is almost equal to IC. This beta over beta plus 1, we show it with alpha. And alpha is usually very close to 1. This is the operation of the transistor in the active mode. As simple as that. We are going to solve problems. We're going to make sure that you understood it. But now I just want you to understand the basics of the operation. Here in this table, I have plotted a summary of the BJT current voltage relationships in the active mode. You see all of these things are here. IC is beta IB, IE is IC plus IB, IE is 1 plus beta IB, or IC is alpha IE, and alpha, which is beta over 1 plus beta. So this is for your reference, that you're going to have access to this later on in your exams and these things. You're going to have this table in the active mode. So this is the main thing that we learned about the active mode of a transistor BJT. Let's quickly look at this example. Imagine you have this, what kind of transistor is this? Right, NPN, right? The arrow is down. So imagine you have connected this to 10 volts, okay? And then there is a resistor at the collector. Also there is a resistor at the emitter, and the emitter is also connected to a minus 10 volts battery. Base is being grounded. So the question here is to find all these currents, IC, IB, IE, and also find VC. Look, usually here it says find VC, but usually when we solve a problem in transistors, they ask us mainly to find VCE and IC. So the current in the collector is important, and the voltage between the collector and emitter. These are the main two parameters that they always ask us to find. So when you find these two parameters, it means you know you have a handle on the transistor. So I let you think about it yourself. I've written the final answers for you, and I give you a hint how to look at it. Look, you remember I told you this thing works like a diode. So if here is grounded at 0, it means here has to be minus 0.7. Absolutely. So if here is minus 0.7, here is minus 10, can you find this current? Yes. It's easy, right? This one minus this one is going to become 9.3 over 10k. So you're going to get this current. And also you know that beta is 50 here. So if you know IE and you know beta, you can probably tell what is IB and IC. You remember this, right? You know IE, so you can find, and you have beta, so you can find IB. And also you know IE, and you have beta, so you can have alpha, so you can have IC. And if you have the current here, so you can find the voltage here as well, so you can find VCE as well. So try to do it yourself and make sure that you will get these values. I think that's enough for today. I'm gonna explain more and more for this transistor. It's really a very cool topic, and I want you to master it. So please, if you watch this video, I invite you to watch it once again, and I invite you to make sure that you will solve this example, get these numbers. If you got even a 0.1 value different than this, come to me and ask me the question. I want to explain to you how it works. Thank you very much. Have fun. Take care.